Hello everyone, I am Ken Asselman. I am a senior researcher at the Royal Military Academy in the Robotics and Autonomous Systems Laboratory of the Mechanics Department. And today I will present an overview of current challenges and ongoing research projects in our lab in military robotics, covering ground, air, and maritime domains. This presentation highlights common technical bottlenecks encountered when deploying robotic systems in real operational environments and will illustrate our current research projects' attempts to address those challenges. I will start with ground robotics with an emphasis on demining and counter-IED operations. Then I will devote a part of the talk to aerial systems before discussing maritime robotics and cybersecurity of robots. I will then conclude with some cross-domain challenges and broader perspectives. So our plan for today is, as I said, an overview of key challenges in ground robotics and demining, then air and maritime robotics applications, and some conclusions and Q&A. So to give a bit of context, in this slide you can see part of the projects that are currently running in the Robotics and Autonomous Systems Lab, from Belgian Defense to the European Union or other sources of funding. Robotics in defense context faces the same fundamental challenges as robotics in general, ranging from perception, autonomy, manipulation, coordination, and human-robot interaction, but under very strong constraints. The systems that we are making must operate in unstructured environments, indoor or outdoors, with incomplete information, sometimes also unreliable communication, and under strict safety requirements. The robustness and deployability and the trust of the operator is very central in our design objectives. Let's start with some example in ground robotics first. So in ground robotics, one particularly important field of application for us, and that illustrates very well our research and the way we tackle challenges, is demining and counter-IED operations. Landmines and improvised explosive devices remain a major cause of casualty, with civilians representing the majority of victims. Detections of landmines and improvised explosive devices is very difficult due to the diversity of different design types, triggering mechanisms, and material that can be used to make those explosives. Operations are still typically slow, manual, and very dangerous for the operators. One of our objectives as a robotics lab is then to bring more robots to this field and try to automate as much of the task as possible to reduce the risk for the operators and also improve the situational awareness for them. So improvised explosive devices are one of the most dangerous of those devices. They can be virtually made with anything. In this slide you can see some of them made with old metal shells, drones, pressure cookers, plastic bottles, and the triggering mechanism can be cell phones, walkie-talkies, or just simply wires. They are very difficult to detect because of the variety of the material used to build them. So this is one of the most difficult and challenging tasks that we are facing right now. So in demining and counter-IED, we are actively collaborating with the Belgian demining team of Dovo, and we try to leverage robotics systems for faster and safer operations. Right now, so to sum up, the available challenges is the automatic detection and landmines and their disposal, the autonomy of the robots in very unstructured environments, so it could be full of grass or gravel or any disturbed terrain. Also doing this with multiple robots at the same time and making the robots collaborate. And also, how do you control the robots and how do you handle the communication between the robot and the human that controls the robots? So we have three main projects that are running in terms of detection of explosive devices. ADET was the first of the three. It is currently finished, but ADEX and Convoy are the follow-up of this one. The ADEX project focused on trying to leverage artificial intelligence for the detection of explosive devices. This core idea was to combine different sensor modalities and fuse them for the detection of explosive devices. Building on this foundation, the ADEX and Convoy have been follow-up projects that extend ADEX toward a larger scale network multi-robot system. In the ADEX project, one of the objectives was to bring the system to a higher level of readiness compared to ADED. This project is part of a European technical challenge, which means that there are multiple consortia that are building a system for the detection of explosive devices, and a consortia is organizing every year some tests to see what are the readiness of those systems and compare the performance over the years. This project involves sensor fusion, multi-robot cooperation, shared mapping, and real feedback on threat localization. So the idea is really like to leverage this multi-robot systems with a lot of different sensors, both air and ground, and those robots should share their sensory information in order to build in real time a map of a threat that can be detected on the field during an operation. The Convoy project further extends this approach by introducing a cloud-enabled architecture and the integration with command and control. This project investigates how data from multiple platforms and from soldiers could be fused through a tactical cloud. The key challenge on this one include interoperability, communication constraints, and the integration in existing battle management systems. In this slide, you can see some of the results we obtained during one of the test campaigns. On the bottom of the slide, you can see the images with the trajectory of the robots and the detected threats that are small dots on the map. Tackling other kinds of challenges is the Belgian project, which deals with mobile manipulation for demining. So in this project, the challenges are the difficulty to pilot demining robots, especially when it concerns the manipulation. So you need a lot of training to pilot and control robotics arm successfully. And the current tools that are used to control the robotic arms are not intuitive and insufficient for very complex manipulations. So the objective of the Belgian project was to develop intuitive teleoperation systems to interact and control the effectors on the robots. You can see in here the example of a flowchart of the systems. So you have the robotic arms, which is attached with sensor. These sensors provide some onboard sensor processing that are both AI-based or feature-based, and all of this is installed on a UGV platform that has an arm. On the base station, you can also have a robotic arm control and virtual reality for the operator to use and get augmented information from the sensor processing from the robot. So the idea is really to use multiple sensors like cameras or lidars, use this data and give feedback and insights to the operator in order to enhance their situational awareness and the precision of the control that the operator has on the robot. When it comes to man-unmanned systems and interoperability, the IMAX project is one project that investigates these challenges. The IMAX project itself is finished, but we are now starting the IMAX 2 projects. I will show you a quick video of one of the demonstrations we did for the project right now. So this video illustrated the challenges in INMUX, where we investigate fleets of robotic platforms supported by human-operated vehicles. The key challenge is here multi-robot and multi-objective decision-making. Rather than controlling individual robots, the operators must supervise a coordinated system that resolves conflicts and adapt to changing mission objectives. We will now move to aerial robotics, where autonomy and robustness are also very critical, but constraints take a different form, in particular when it comes to GNSS-denied or GPS-denied operations, which is right now a very central topic. One of our project is the GRAND project, which stands for GNSS-free autonomous navigation for drones. The idea in GRAND is to focus on GNSS-free navigation. In contested or degraded environments, the reliance on satellite navigation is not a realistic assumption. In GRAND, we try to investigate alternative navigation strategies that are based on onboard sensing, like LiDAR or images. This enables drones to operate autonomously and independently of external positioning infrastructure. The main challenge in here lies in maintaining localization accuracy over time wherever the drone is flying and ensuring the robustness to potential degradation of the quality of the sensor readings. Another aerial project that focuses on one of today's challenges is the Hadron project. In the Hadron project, we face the problem of human-friendly control of drones. So the idea would be to combine intuitive interfaces such as voice commands or motion sensing, and together with some data interpretation and AI-based perception, the objective is to enable untrained users or expert operators to interact efficiently with single drones or groups of drones, depending on the mission context. In the maritime domain, scale and environmental uncertainty dominate the problem. Continuous surveillance of large maritime areas is infeasible with manned assets alone. That motivates the use of autonomous surface vessels. The first project we're going to present today is MARSUR, Maritime Surveillance Project. This project focuses on maritime surveillance using autonomous boats. The objectives include the patrol of restricted areas such as wind farm parks or any critical offshore infrastructure in order to detect intrusion and support situational awareness. The main challenge involves a long-duration autonomy, perception in long-range cluttered maritime environment, and reliable human-machine interaction for the supervision of the boats. For this maritime project, we are also developing our own rubber inflatable boat based on an off-the-shelf boat that is augmented with autonomous capabilities in order to surveil these areas. In the MARSUR project, there is also a strong component about boat simulation. The idea is that having a very realistic simulator allows two things. First thing is to train algorithms to control the boat and control its planning in simulation so that we can prepare the missions in advance and test whether this mission would work. And the second one would be to create realistic scenarios where you could have a digital twin of the robot on your computer while it is operating live on the field. And here you can see a video of some of the field tests that we did for the MARSUR project. The last maritime project I'm going to discuss is the Multimeter project. autonomous unmanned vessels for maritime mine countermeasure operations. The Multimeter project addresses mine countermeasure operations. This project integrates a multi-beam echo sounder for underwater mapping, but also integrates long-range navigation and mapping. The key difficulty lies in managing the high volumes of sensor data under very limited communication bandwidth and constraints, which pushes towards a lot of onboard processing and very selective information sharing with the control center. Lastly, I will discuss the Forces project. The Forces project addresses aspects of robotics that are in the transversal domain, and specifically about the security of robotic systems. As robotic systems become more autonomous, distributed, and interconnected, the idea is that security becomes a very critical asset. In Forces, we investigate methods and frameworks to improve the security of robotic systems and architecture. The idea is to migrate from C and C++ code to more memory-safe languages like Rust, and to do all of this automatically. Among the open questions of Forces is how does transpilation allow for enhanced security without any performance cost? This is one of the most pressing questions. Also, does software need to be migrated, or simply checking for memory safety is sufficient? And also, what are the different migration techniques, and how do they compare with the new paradigm of generative AI in order to change from legacy code to more safe embedded code? In conclusion, across the ground, air, maritime, and cyber transversal robotics domain, a set of recurring challenges emerge. Robust perception through sensor fusion. We have more and more data, and we need to use them and to fuse them in order to get more qualitative perception and situational awareness. Autonomy in unstructured and uncertain environments. Scalable multi-robot coordination in order to be able to use multiple robots at the same time so that they can effectively collaborate and cooperate. Effective human-robot interaction. We need to be able to control the system and to do it in a very easy and secure way so that even untrained personnel could use them. More broadly, these projects illustrate a shift from isolated robotic platforms towards complex, heterogeneous, and cooperative systems. This shift requires not only technical advances, but also new methodologies for design, validation, and development. For sure, bridging the gap between research prototypes and operational systems is therefore a very central and critical challenge that is still open for military robotics. Thank you very much.